Welcome everybody to our webinar session. We are very excited about having you today. We will start soon, but first we will mention some points related to the organization. Your microphone is on mute. We will keep this feature as it is to provide an organized session to avoid background noise and interruptions during the presentation. However, we have a messenger option. In the bottom of the screen, you will see an icon. You can submit written questions by typing them in the question box in your control panel. We would like to have an interactive session and discussion, so please feel free to send your questions. You may send them at any time, and we will collect and address them at the end of the presentation. In case the presentation takes longer, we will extend the session 15 minutes so we can discuss your questions. You will be able to count with the presentation that will be shown during the conference. It will be sent by email on PDF right afterwards. Now, I would like to introduce our speaker. Mr. Christian Höfels is Process Technology Development Specialist at Netzsch. He holds a bachelor and a master's degree in process engineering. He is in charge of new trends and optimization in all kinds of processes, starting from trials in the test lab to the construction and up to commissioning and optimization of the plants in industrial operation. About the company, Netzsch is specialized in ultra-fine grinding and classifying. It offers extensive experience and a very varied machine program ranging from laboratory and production machines to complete manufacturing lines. The company has one of the most modern application lab centers in which grinding and classifying technologies are available for carrying out tests with customers' products. About Weibold Consulting, the company was founded in 1999. Over the years, Weibold gathered an international team of experts and established a large professional network involving researchers, decision makers, and authorities. In addition, Weibold issues a free monthly newsletter on tire recycling and pyrolysis, which relates to all aspects of these industries and provides unique takes on the newest developments and trends. We hope you enjoyed the session. Christian, please, whenever you want.
Yes, hello everybody. Also from my side, I'm very pleased that I get the chance to speak today here over this nice platform from Weibold, and I want to discuss the topic of fine grinding of recovered carbon black, and especially fluidized bed jet mills will be in the focus, but I will also give you some words about different technology which are state of the art in the fine grinding. First of all, I want to introduce additionally to the words Augustina mentioned, some points about Netzsch, and then later on, of course, start with the fine grinding of RCB, and then give you some examples and references of already applied plants on the market, and at the end, of course, a summary about this topic. So first, about our company. The company has a holding on top with 3 big business units. The first one and the smallest one is analyzing and testing. It's also very close connected to the rubber industry. Maybe you know about thermal analysis of gravimetric analysis of TGA, or the thermophysical properties for rubber testing. And on the other hand, the biggest part is pumps and system. For example, in the oil industry, we have the positive displacement type pump Nemo, which is one of the market-leading technologies. And here in the middle, maybe 1/3 of the income of the turnover of the company is grinding and dispersion. That is the unit where I come from, and this unit makes wet and dry grinding equipment, like as well with mixing, dispersing, and homogenization products. And I am from a unit which is specialized on dry grinding and dry classification. So here you see the turnover in the last fiscal year. It's 500 million, and our employees is close to the 4,000 employee market, and we are nicely growing over the last years. And like mentioned before, here are the business units, and you see grinding and dispersion is 1/3 of the turnover. We have roughly 150 years history, and the company was founded by 2 brothers in Zelb, and right now it's the 5th generation of the Netzsch family with Paul and Moritz Netzsch on top of the holding. And together with Jens Nisser, they are leading the company and the business units to the actual path. The business unit grinding and dispersion is organized in 4 business units: the chemical industry, the food and confectionery, the pharmaceutical and cosmetics, and the mineral and mining unit. And for us, RCB, or at least carbon black, is in the field of chemical industry, together with, for example, battery masses or liquids, paints and coatings, and things like that. Our business unit has a sales volume of roughly 180 million, a bit more than 1,000 employees, and various production and laboratories worldwide, and also a lot of sales and service locations to be always on site if the customer needs any help or any after-sales service. So now to the core topic about efficient grinding of recovered carbon black. So during the last webinars here at Weibold, for example, I learned a lot about the pyrolysis steps, and this is, I would say, the state of the art, a very simple picture, simple image. We have the end-of-life tires, which going into the pyrolysis, and with the absence of oxygen and hot temperatures, and we have the pyrolysis process, and you get 3 volume streams out of this pyrolysis. And the main and often the focused product is the oil and gas, which is very valuable and can be sold on the market. And on the other hand, you have a lot of steel wires, which can also be collected and sold on the market. And on the last hand, we have here the recovered carbon black. And if you have no further processing of this stream, it's more or less a waste stream, which is often sold in the, for example, as a secondary fuel in the cement industry, where you get maybe roughly 50 euros per ton. But here, the big margin, if you have a fine grinding step here, this is exactly where we come into the process, which is our challenge to find the right technique to make a nice fine grinding step inside of this project and bring it to a certain finest level where you have a much higher value than you create easily, maybe 500 euros per ton value, or even more. In some special applications, you can reach easily up to 1,000 euros per ton. So the first challenge is to choose the right machine. On this picture, you see all the machines we have in our portfolio over the working size. So here's a particle size of the end product, which is reachable. And here on the coarse end, we have a lot of cutting mills, for example, for cellulose or from fiber materials, which can be grind. Or we have the impact mill without any classification, just a pin mill, which works maybe down to 30 or 50 micron in a top cut for the end product. And here on top, you see the classifier mill. It's a mechanical mill, but with a variable classifier. This can reach maybe down to 10 micron for the cut. This is the first machine which hits the targets for RCB on the market. I learned so far that we have 10, 20, and 30 microns, depending on the application, which are the main focused qualities on the market. And this machine could hit all the targets. Even finer, here our fluidized bed and high density bed jet mills, which can also operate much finer. The steam mill can reach maybe in the nano range, but we don't need it for the application, but it's still a good machine working in this range. Another machine here down there, it's a dry agitated bead mill. This works with friction a lot in grinding media, so this is maybe not the perfect machine for this application. And here we have 2 classifiers which cannot grind. We're just classifying. So these 4 machines, or those 4 types of machines, seems to be fitting for our RCB applications. First, I would like to introduce the classifier mill. Here we have a sketch, and we have the under pressure here behind the mill, where the product is sucked into a filter, and this leads to a volume stream of air here inside of the mill to the housing, through the scab, along the guide vanes to the classifier, and then, like I mentioned before, to the filter. And on the other hand, we have here this grinding disc, which is rotating with hammers on top, and they are turning, and they're making the impact and movement of the product. And this leads to a secondary stream, which is around those guide vanes, and this a small circulation load, and the product, which is falling, for example, through this inlet 1 into the mill, is taken into the secondary stream and offered to the classifier, where the fine product can leave the system, and the coarse is falling back into the secondary stream, going over the hammers and over the grinding track. It's grinded again and is moved here several times around. You see it here for a small machine. We have here the hammers. This can be in several executions. For example, hard metal or alumina executions are also available to have a good wear protection, but it's a mechanical mill, and you will suffer a lot of where if you have crystalline products, for example, silica, normally for us it's a border if you have 0.5% silica in your product, we wouldn't recommend this machine, even if it's good in a good execution with hard metal or aluminum oxide to provide the wear as good as possible, but we wouldn't recommend such a mill for those applications where you find a lot of abrasive products. On the next slide here, you see at least the advantages of such a machine. So we have a very nice oversized controlled particle collective after the grinding because we have a variable classifier on top. We have a long lifetime due to the bearings which are protected with purged air, and we have a nice possibility to access from the top. You see here we have a double shaft system downwards here. So if you open the mill, the top of the mill, you can easily access the classifier wheel and inspect it, or even for maintenance, remove it easily. Then we have separate drives. Here this drive is for the grinding disc, and here the second drive is a bit hidden behind the machine. This will turn the classifier, so you have all variables to optimize the process easily to your application. And it's also possible to take this machine as a pressure shock resistant execution or a gas tight execution if necessary. But like I mentioned before, in terms of wear, you have to be carefully if you have hard products or impurities in your mill. We wouldn't recommend such a machine, and for RCB this is the case. So often in virgin carbon black this machine is used, but for recovered carbon black we wouldn't recommend due to the silica content and even the crystalline silica, which is still remaining in the tires from dirt from the streets, for example, will cause some wear problems inside of this machine. The sizes can be various. All our machines are available in lab scale, like you see it here behind the stainless steel container. Here we have a blower inside, so it's a completely plant where you see the mill here. Then we have maybe a cyclone if necessary and a small filter unit. And here behind the machine you have a dosing device, so this can operate completely automatic in your lab scale for feasibility tests, or just to produce some qualities to test the applications later on. Or you can go up to really big production scale, like you see it here, with very nice throughput ranges for big mass products. So then the next step is jet milling. First of all, the definition. What is jet milling for me? Jet mill is a process equipment with use of fluid under specific pressure and temperature. And in our case, it's gas or steam, or the gas is normally air. And this gas is expanded through jets, through nozzles, into a grinding chamber, and then the particles are accelerated by these jets and is crushed by impact with each other. So it's autogeneous grinding, and you have no wear due to the grinding process. And we have two different types for this kind of bed mills: the fluidized bed jet mill, CGS or S-jet, or the high density bed jet mill from the type conjet. And here you see the differences. On the right side here we have the high density bed mill conjet, and in this blue ring we have the high pressure gas supply, which is expanding through this nozzle, and the particles which are falling through this pipe into the grinding chamber are taken into these nozzles, grinded, and are offered to the classifier wheel, which you see here in the middle, and the fine particles can leave the system and the cores are rejected and falling back into the particle stream, which is in the vortex around the classifier wheel. This execution is very nice if you have frequently changing products where you have to open the mill and you have to clean it, because we have a very small grinding chamber and it's very quickly empty. If you want to stop, you just keep the mill for several minutes running without any feed, then it's nearly empty, and you can you have no losses of product. Even if you have, for example, pharmaceuticals, which can also be a problem for the health. If you open it, then you have nearly no product remaining, and it's easily to clean it and to maintain it. But this is more for specialties, and for a mass product like RCB, where you try to run the machine the whole year with as less stops as possible, we would recommend to use the fluidized bed jet mill from the type CGS, where you see here again the pressure supply, which are expanding here in the grinding chamber, and the particles which are falling in this bed are grinded, taken to the classifier, classified, and the course is falling back, and the fine is leaving to the baghouse. But that will be explained much more in detail on the following slides. First, the stress what the particles will see inside the jet. So the first stress is just on a single nozzle. We have the jet, and the particles will enter over the surface or just enter the surface of the nozzle, are accelerated. And for example, in this case, you have here a fast particle which is already in the stream, and another one falling into the stream, and this will be hit by the faster one from the back. And there we have the first impact and the first stress in the particles. And on the other hand, we have the opposed system where the streams will hit in the middle with a nicely adjusted distance between the nozzles, the center. The air will easily go to the other direction because there's nearly no mass in comparison to the particles, and the particles are following with the mass their acceleration, and they will hit each other here in the burning point of the system, and there the next stress and the next breakage will occur. And the velocities you find here are very high, approximately 600 to 650 meters per second, are easily reachable with the systems. So you see the potential how fast the particles can shoot to each other and can be grinded. Maybe 70% of the grinding takes place in the single nozzle, and only 30% are taken here in the focus point where the particles will hit. So also the streams and the surfaces of the nozzles are very, very important for our grinding. But now some more words about how we operate such a mill. If I started now, you will see the pressure and the gas will expand through the nozzles and leave to the classifier, and the product is falling here in the fluidized bed level. And when it reaches the nozzles, it will be grinded and taken up to the classifier. Maybe you see here the level of the fluidized bed is not constant yet. Of course, the fine particles will leave the system, so the level will set down, and we fill it with the feed to a quite constant level. And the first challenge is to keep this level as constant as possible. And if we have a heavy product, we do it by the mass of the whole system. So we control the mass, and we calculate how much fluidized bed level has to be inside here, and we keep it very constant with set points in our PLC. But for lightweight products, like example with RCB, if we have 100 gram per liter bulk density, it's not always possible to control the whole system with this mass control. They need a different set point or a different value, and this is the amperage of the classifier. Here we have this belt drive classifier with the engine, and if the system is very occupied and very full by product, the amperage of the classifier will be much higher than before. So we can use this as a set point. And for this, our first advantage is, of course, a single classifier design. So you see we have only one classifier in the machine, and we have only one engine to control. So this gives us a very accurate set point. And another big advantage is if you see the flow, it's rising up from the bed, and it has to go around the fines outlet beneath the classifier wheel. So it's very nicely separated, and here it's coming with a good dispersion to all sides of the classifier, very constant, and this gives you a very constant top cut, a very good control of the quality, and as well the wear. This is the only part where we suffer with wear, is the turning classifier wheel. As this will be also very constant. So at least if you have wear, you should try to keep it as constant as possible to have a long lifetime and long good maintenance period for a classifier wheel. Then another advantage is, I will later on explain why you should hot gas here in this operation, is the bearing. We have only one bearing due to the fact that we have only one classifier wheel on top, and this bearing is not grease lubrified, this is oil lubrified. Because the grease will also be heated by the whole system, and then the lifetime will be dramatically shorter than it should be. And with the oil lubrified bearing, we have maybe 3 times the lifetime in comparison to a grease lubrified bearing. This is another very good advantage of the single classifier design. Another point is to mention is also the way of the gas to the nozzles. We have a very wide piping here with this turbulence reduced design. It goes directly from this supply chain down to the nozzles, and it expanding here quickly into the chamber. So the compressor should be as close as possible to the system, and then with very wide diameters, you have no pressure drop over the piping to keep a very accurate and very efficient pressure supply. And the last point I want to mention is the fluidized bed level. This can be opened with this bottom opening, and if we have, for example, some steel wires remaining from the process step before, or some heavy impurities, it will settle down and lying here at the ground of this fluidized bed level. That with frequently opening of this nozzle, you can take these impurities out, and then the quality of your RCB at the end will be much higher than the feed which is going into the system. So that's for the operation. And I want to continue with the new systems, Ester and EJET. So the question was, maybe 30 years ago, is the standard operation mode of a jet mill very accurate and very the best what you can reach? We have always high pressures, normally 7 to 9 bars maybe. You have quite moderate temperatures, and the discussion with customer and with the industry show that's not the best way. You're always forced to go with efficiency. You have to reduce your carbon dioxide. You have to reduce your efficiency in terms of money. You just save money if you save energy. So we need a new system for optimized energy usage. And the answer from Netzsch was the EJET system, and as well to be even in low finer range, or even to be more effective, we have the Ester system, which is for steam application. And those systems I want to explain over the next minutes. So the EJET system, first, to understand why we optimize the compressor, you have to look at the whole system. Here we have our mill with the 4 main electric drives, I would say. We have here at the end the backhouse blower, which make under pressure in the filter, to suck the product from the mill in the filter. On the other hand, we have the feeding device, which are bringing the product into the mill. And here we have the classifier engine, like mentioned before, which is turning the classifier. So these components are not so big in comparison to the compressor. The compressor is a very, very big energy consumer, and you have to go with this one if you want to save energy. So normally positive displacement machines are used. For example, here's one sketch from Atlas Copco, and the screws are turning into each other, and the gas is compressed, and you have a dramatic temperature increase over such a screw. And here at the end, for example, you have 3 bar and 200 degrees Celsius. If you want to reach the conditions, like mentioned before, from 7 or 8 bar, you need a second stage. The second stage cannot handle the high inlet temperature of maybe 200 degrees, so you have to use the intercooler to bring it down those to ambient conditions, and then you can go with your high pressure again into the second stage and create the conditions what is required for your application. Maybe this diagram also shows this problem. So it's also from Atlas Copco. You have here the first stage and the second stage with the intercooler, and here you have your normal treatment for a pressure, so for a high pressure net. The aftercooler is a refrigerant dryer here at the end, and here an absorption dryer in the middle. So you go into the first stage with ambient conditions with nearly 0 bar gauge, so 1 bar absolute, and ambient temperature of 20-25 degrees Celsius. Then you increase the pressure up to 3 bar gauge, so the temperature is also rising up to 160-170 degrees, and there you need the first intercooling. You go down to 35 degrees, and then again you increase the pressure and the temperature. Then you have aftercooler and so on, like mentioned before. And this both cooling steps, the aftercooler and the intercooler, are a massive loss of energy. This energy should be used in the process, otherwise it's a waste. This becomes clear if you see what energies we have on site during our grinding steps. So first, the energy which is available for grinding. This is the kinetic energy of the gas behind the nozzle. So you can calculate how much energy you use after the explanation. And on the other hand, we have the work to create this kinetic energy. And this is the value from the compressor manufacturer. Because this is hard to calculate. We have a lot of mechanical efficiency in this machine, so we cannot calculate it with thermodynamics laws like this one. So we have to use the empiric values from the compressor manufacturer, but they have a very big database, so it's also very accurate. And with these two values, the energy which you are putting into the process and the energy which can be used in the process, we define our efficiency. And here you see the single stage machines. If you use a high temperature, you can create maybe 70% efficiency, which is quite good. And here in the second chart, they are two-stage machines from 2 suppliers, and the first one is using 160 degrees at the end, and the second one is using 200 degrees. So maybe if I go one slide back, they just spare the aftercooler. So you need this intercooler because the second stage cannot handle this high temperature which are coming from the first stage, but this aftercooler can be thrown out of this project. So you just have the intercooler. So this is why we have this dramatic loss of energy. But at least if you take all the energy from the second stage into the process, you have a higher efficiency. And you see the supplier A is not possible for him to take all the energy from the first step into the second, or not so much energy into the next step than the supplier B. The supplier can end up here with 200 degrees instead of 160, and you see directly the change of the efficiency. To make it a bit more clear, here on the next slide, you see another chart, and here you have the energy on this axis, and this is again a single stage and a two-stage machine. So you can have a look if you want to create 3 bar volume, and all those curves are for 1,000 norm cubic meters. So if the compressor with single stage creates 3 bar 1,000 norm cubic meters, you need maybe 75 kilowatts. And this 75 kilowatts, 1,000 norm cubic meters are going to a mill, and there you can expand this and you get a certain energy back. That is exactly what we have done before with the efficiency. If you expand this 1,000 norm cubic meters at 20 degrees Celsius, you get 38, maybe close to 40 kilowatts out of your process. But if you expand the same amount, 1,000 norm cubic meters at 200 degrees, you have a much higher volume due to the process conditions, and then you can get back 58 or close to 60 kilowatts. So this shows exactly what eGET is about, where our focus lies. So we try to take a single stage machine, go as high as possible with the pressure, and take as much temperature as possible into the process to have a much higher process volume than you would have at lower temperature. So I want to summarize the eGET concept. We have a one classifier wheel in our machines. This is a factor for constant product quality and reproducible fine cuts. It's easy to maintain, and it's steady and low wear. And we have a high efficiency due to the flow optimized machine design. And we have a patented nozzle distances for hot gas operation to have efficient setup. And we have a temperature stable bearing for high availability. Now the Ester system. So there's always the first very important question: why should we use steam instead of air? And this is a very simple image just from Wikipedia from a power plant. In this case, it's a coal power plant, but it doesn't matter if it's gas or even nuclear power. I think it's very similar for all kind of power plants. We just create very nice heat here inside. Then we have maybe thermal oil to create to take the heat away. Then we create steam, and the steam is going over a turbine, and the turbine turns a generator, and then we have electricity which can be transformed into the net, and then easily spoken on site of your plant, you can plug in your compressor and create your eGET system. But already here, after the transformation of energy, we have maybe 36% efficiency. So this have a loss of roughly 60 to 70%, and this is a malus. This is a carbon dioxide backpack which we already have when we plug in our machine. So why shouldn't we stop here at this stage? Where we have 90% where we burn our fossil fuel, have thermal energy, we are creating steam, so we have a gas with high pressure and high temperature. This is exactly what we normally reach with our eGET system. So we can stop here with the efficiency of 90%, which is much higher than everything what we can reach down here, because we have here the mechanical steps of our power plant in between. Our standard conditions which we are using for the SJET system is normally 40 bars, but if you go higher, you are even more effective. For example, in the US, we have plants which are operating with 100 bar pressure. It's also possible. And we expand the gas over our nozzles, and then with the internal pressure of the mill, we end up at 1.1 bar pressure and maybe 300 degrees. So you see we are again much above the phase boundary. We are still in the saturated area. In the overheated, not in the saturated, in the overheated steam area. So our particles never see any moisture. They are kept very dry all the time. So this is an isentropic expansion, and the enthalpy, like you see it here, is nearly the same. Only the entropy, which is used for the grinding, is changed. And even at the back of our filter, we have 120-degree minimum, normally a bit more, to be sure that we never have any condensation inside our process. Here's a image of a certain steam and product temperature improvement. So we have here our whole steps over the mill, and here we have the temperature in red from the product and in blue from the steam. So at the beginning, where the steam goes to the piping coming from the boiler, we have 350 degrees for the steam and maybe ambient temperature for the product. And up at the nozzles, we have some losses over the piping, and the temperature of the product is still the same because they have in contact with the steam. And then we're expanding the steam through the nozzles. There we lose, due to the expansion, a lot of temperature. And here we have the first point where they have contact with the product. So we have a heat transfer in the later on points, and we are mixing the product with the steam, and it's grinding and it's pressed, and the temperature is rising of the product. This is the temperature of the steam is coming down. And here at the filter, both components like product and steam are separated, and the steam is going, like mentioned before, with 120, 130 degree over the blower into the environment, and our product can cool down back to the ambient conditions. So a very important point is the steam supply. So we take the steam, if necessary or if available, from the steam network. That would be the perfect conditions if you're maybe on a big industrial area, or if you are operator of a petrochemical industry plant, then you have often steam network on site. This would be the perfect solution. Another very good solution would be if you have an existing saturated steam network, then you can install a locally superheater to get the steam in the conditions that you really need. Or the last possibility is also possible. You have a separate boiler which is directly linked to the plant. This is, for example, what we are doing in our test lab. They need some components I will explain later on. And of course, you need a fuel. Electrical is normally only used for test lab plants, because then you have not the efficiency bonus like I mentioned before. But oil and gas in general is taken. And that's also very interesting. We can maybe discuss it later on. Even in the RCB process, in the pyrolysis, you have a lot of gas, which is maybe not possible for sale. And I know that some of the plant operators maybe burn it in a gas engine to create electricity for their steps, or even to sell the electricity. And this is also a nice option. Maybe you can switch this and change the gas as directly as a fuel to your milling step. But now the steps in our test lab, we have a very nice water condition unit, feed water tank, high pressure pump, then the steam generator with the economizer for the steam which is coming back from the superheater, and the superheater which is going with these conditions to the mill. And this was very wide installation because it was our first one, and we have plenty of space, so we made it easy to maintain and easy to change something. Right now, if we have an industrial plant, we have it much more compact, like this installation on a skid. You can use it in a container, and it's easy to operate and easy to commission on site of the plant. So we have a water treatment and the feed water tank with all the pressure boosting, like the high pressure pump here, and then the steam boiler and superheater as a second unit. And yeah, it's very nicely and compact already. So the summary of the Ester system is nearly the same as the EJet, because everything like the single classifier wheel and the autogeneous grinding stays the same. And additionally, we have much higher pressures and much higher velocities, so we have much more energy in the system. So we have double the jet velocity. We can reach much higher values than 1,000 meters per second. And this leads to the fact that the capacity of a mill with the same size can be much higher than the capacity of a normal jet mill which is operated by air. Then the efficiency is on basis on primary energy much lower, or the energy consumption is much lower, so the efficiency is higher, and this leads to a much better CO or carbon dioxide emission over your process. And existing steam network can be used, or better would be should be used, because if you have already steam on site, this is a perfect solution for your application. Now a short comparison of steam and air. Maybe just the technique at the beginning. Here we have the mechanical compressor and the thermal steam generator. And I think the most important point is that the generated heat in both systems can be used. Here we should use it for the EJET system, and here it can be completely used because the burner or all the waste heat is also nice to increase the temperature of our fluid from the inlet side. And the pressures are a very important point because here we are limited due to mechanical factors, and here the higher pressure are achievable, and even the efficiency for the steam will be higher with higher pressures, and here the efficiency will be decreased by the intercooling steps for higher pressure and for mechanical losses. Okay, but this is more academic point of view and always about energy, but that's normally not the important point for industrial applications. We always go after the money, and this efficiency can be also directly transferred into money. But here first you see the efficiency for the primary energy, and even if your electric drives on the plant for the EJET system are nearly perfect, then you at least have the same efficiencies in the power plant than the electricity you get. And here the 90% can be directly influenced by your process, by your steam generator. But now the promised chart for the costs for such a comparison. So I take a fictive number for a 3-ton RCB plant, which can be operated with one air mill. We have a feed size of 2 millimeters, for example, and the product size should be everything below 10 micron. And I took the same identical specific energy for both systems, for the EJET system and for the Ester system. And I discussed with a German customer what the prices for the supplies are for energy, for electric energy. He told me that's 0.1 euros, so 10 cents per kilowatt hour. And the operation would be EJET system with 3.2 bar and 220 degrees Celsius. So the operation cost just for the grinding step, without any force and back steps, just for the grinding would be 22 euros per ton of RCB. And for the Ester system, the same customer told me that you have an internal cost factor of 20 euros per ton steam. And then you can operate our standard conditions close to 40 bar gauge and 320 degrees Celsius. And there's the operation cost would be 15 euros per ton. And one very interesting point is here, like mentioned before, this cost should be directly checked by yourself. So if the steam maybe is much cheaper because we have some liquid oil or even some gases which can be burned on site, maybe your cost will be dramatically lower. One also very important point is this is the costs what I get from the customer. This is for the whole steam process, so also with maintenance, with personnel working in the steam plant. And here this is just the electricity, and you have to operate the compressor as well. So this compressor needs also maintenance and maybe also some personnel to check it. And these costs are not included here, but they are also included here. But they are already in this 20 euros per ton. The wear for both systems would be comparable, I would say. So the classifier wheel will last in the similar range for both systems. But another advantage of the Ester system would be, like mentioned before, the footprint of the plant for the same throughput will be smaller. So you need a much bigger air mill in comparison to a steam mill to create the same amount of recovered carbon black. So this is also one point to mention. So, but now I come to some examples and references, or two, to be correct. So the first one is, I would say, a medium sized machine. It's a CGS71 with 2,000 cubic meters gas volume. This is an EJET operation for hot gas and 3.2 bar gauge. The target of the customer is 7 micron, and the throughput, which we was guaranteed, which is in the reality a bit higher, was 500 kg per hour. And you see here our measurement. It was done with a Malvan Master Sizer 3000 in dry operation mode, and you see with the D99 with 6.5 micron is perfectly hitting the target. So this is a nice machine in operation. The next picture is a bit bigger thing. Two machines just in parallel, and you see we have a pre-grinding step and feeding to this device, and you have the screw feeder here to separate the product stream to the one or the other mill, and both machines are independent from each other, so you can produce one quality with the one and another quality with the other. Of course, you can produce the same quality like in production schedule as preferred. Also, these machines are higher with 112,000 cubic meters per hour. It's also operated E-jet operation with hot gas and 3.2 bar gauge. Various classifier speeds are requested, and for the finest point, for the 4 micron, or maybe you see it here on the next slide. Again, here we have the measurements. The guaranteed values was 350 kg each, but if you increase the throughput by the quality, by the product quality, you can increase also the throughput of those kind of machines dramatically. Okay, then another important point, what we learned in our test lab, is also very interesting to mention, is also that the quality influences specific grinding energy dramatically. We have here 2 different qualities of RCB. I call them RCB A and RCB B. And in terms of quality, for example, the process of the pyrolysis is different. If it's a batch or a continuous process, is it 2-step, 1-step? Is it with microwave? Is it with electricity? Is it with gas or whatever? So everything in front influences strongly the quality and also the composition. How high is the silica content? Do you have passenger tires? If you have truck tires, or different kind of rubbers? So everything. How high is the carbonaceous residual? How high is the volatile content? So everything influences dramatically, and you see it very nicely in this chart. So this was, I would say, good grindability for the product. So if you reach, for example, 6 micron in the D97, you need roughly 300 kilowatt hours per ton energy for the RCBA, and for the same quality, for the same fineness, the RCBB needs roughly 1,000 kilowatt hours per ton. So you have the capacity factor of 3 or even more than 3 between these 2 qualities, just due to the differences in your process before. So it's very interesting for us to know as much as possible about your RCB, and it's also for you interesting if you want to make trials to determine out how big your grinding step should be to take the real quality what you later have in the process. Otherwise, there could be a big difference between the checked and the calculated values. Okay, so here you also have a nice overview just for first impression. We have here different machine sizes. We have also lab scale machine, like mentioned before, and we have even bigger machines. But this 4 machines seems to be very good fitting in the RCB world. And you see here roughly what fineness can be reachable. For example, here if you have 10 micron in the D90, you can create with the smallest machine, which we have in our test lab, something around 250, maybe 300 kg throughput, and with the biggest CGS 120, you can create a throughput from maybe 1.5, 1.7 tons per hour. But just, of course, like mentioned before, has a strongly impact with the quality, or the quality has a strongly impact on this chart. So it's just the first impression. So the last slide, just a short summary for all the points I mentioned before. So the fineness of recovered car black is important for the later on applications. So my point of view, you should definitely go with a fluidized batch jet mill. It's a proven technology. It's very wear resistant, and even if it's have a higher invest than comparable mechanical mills, it will be later on a very nice machine, and it's very stable and low maintenance cost can operate your products. Then the 2 systems I introduced to you, the E-jet system. It's a kind of standard machine with a compressor. We have already several systems on the market running, producing with electricity, like mentioned, very good quality RCB. And on the other hand, we have the Ester system. This is not so that's often used right now on the RCB market, but it seems to be very promising. And there we should also do some tests or some proofs if you have steam available on your plant. Then the benefits of our machine and our company is that we have a one classifier design for all our jet mills. This gives you a constant product qualities and the reproducible fineness. It's easy maintenance. Yeah, you can just open the top of the mill and just, for example, with a forklift, remove the classifier wheel just with 1 screw. You need no service, you need nothing. You can do it with your own personnel, maybe in half a shift with 2 advanced operators, and you can change the classifier wheel, just adapt the gap. You can continue with your production. And you have steady and low wear due to this one classifier wheel because we have a nice flow from all sides, very constant to the classifier. We have optimized machine design. We take also care of all the very small details like turbulence reduced design to bring the gas very nicely and very pressure drop neutral, I will say, to the nozzles and save a lot of energy and operation costs even with small points. Then the patented nozzle distance is important even for hot gas operation. We have the accurate distance to save energy and get the most out of your energy what you're bringing into the process. Then temperature stable bearing is also very interesting. We have no grease bearing, we have oil amplified bearings, also adapted to the hot gas operation, and it's a quality point for the long maintenance interval. And we can deliver also very customized engineering solutions for the whole milling process, from the pyrolysis, what you get maybe from after cooler of your pyrolysis to our mills, and then we do everything to the downstream process up to the filter where we can get the fluffy material out and go into the next process step or into the pelletizer. So this can be offered from our side, and hopefully we can discuss now some questions, and I hope I can introduce this technique for all of you. Yes, thank you very much.
Thank you very much. As you mentioned, I would like to share with you questions we received from our attendees. First question: how much recovered carbon black input is required per hour in order to justify investing in your mill?
Yeah, this is a very, of course, it's a very important question, but it's not easily answered. Yeah, because like I mentioned in the introduction, the quality has an impact on the price you can get on the market. So it depends from maybe 500 euros per ton, go up to 1,000 or even more to 1,500 euros per ton. So it's strongly recommended to have a very accurate view on your specific project and what quality you want to reach and what quality you can reach with the pyrolysis you have before. If you have a high quality RCD, then the small amount is only necessary to create high value products.
Thank you, Christian. Next question: how does testing in your company work? Just sending samples? How much would you need? Is there any cost associated with it?
Yeah, of course there are some costs because we do the test for you, and you are invited to join the tests. And maybe this slide is very interesting. Our test lab machine is a CDS 50, so it's roughly in this range. And normally I would say we need half a day for one setup. So if just, for example, specify your target to have D97 or D99 of 10 micron, then we can produce something here in this range around 300 kg per hour. And if you want a very stable run, you need 1 ton of product for such a single point, and then we can make the accurate scale up and say exactly which size for which throughput you would need with your specific RCB.
Thank you, Christian. Next question: what are the pros and cons of using air versus steam as gas?
Yeah, maybe also I can go some slide back to the summary of the Ester system, because I think all the advantages are the same. Yeah? We have this one classifier seal and all the wear and the easy maintenance. I don't want to go through all of them again, but the steam can create more energy into the system, and you have a better efficiency based on the primary energy. But of course, this is a different process. Yeah, you need steam at site. If you have a steam network, I would highly recommend to use such a system. But if you don't have steam on site, it's a much higher system requirement to build up the steam boiler and so on. So there you have to carefully look which is a more optimized system. And I think for all specific cases, you have to check it carefully which one is the best solution. So both are possible.
Thank you, Christian. Next question: Are smaller than CS-M50 lab size machines available? We are interested in capacity 1 to 10 kilograms per hour.
Yes, I can also, maybe I would end my presentation shortly, and you get later on the presentations, and I put some information additionally in this field, so I can show it for a second here. We have here, this is a chart I would like to show you. This is what we are doing, and we have a very wide range, and you see the first two are not scalable. This is our lab machines, and we have the power, it's 1.5 kilowatts installed engine drive power. And with this machine, I think with 1 to 10 kgs, you can do a nice trial. And if you can reach maybe 1 kg per hour, this seems to be a suitable size for such a lab scale machine.
Thank you, Christian. Next question. How does the value of the carbon black differ based on the different size of particles?
I think this is connected to the application where the RCB is later on used. Yeah? I think if you go with 10 or 20 micron D97, then it's for plastic industry, for paints and coatings. And if you have a high valuable product there, you can create maybe higher values. If you create a 30 micron product, for example, for technical rubber, yeah, if you make conveying belts and you just use a small amount of RCB as a blend there, then maybe it's not so worth the money, yeah. But it's also, I think, it's very strongly connected to the feedstock. Yeah? If you want to create a fine product, you need also a very good feedstock and a very good pyrolysis before. So this is. Yeah, everything is very close connected there, and you have to carefully go behind the steps.
Thank you, Christian. Next question. Have you done application with steam jet mill using superheaters equipped with burners running on syngas from pyrolysis?
No, we haven't done it. Normally, we have done tests in our test lab, of course, with conventional burners. Yeah, we have one for a bit smaller plant with 150 kg steam per hour, which is operated with gas, with natural gas, and the other one is with 500 kg per hour steam and is operated with oil. And with both of them, we have done some RCB tests. What we haven't done is with gas from a pyrolysis plant.
Thank you, Christian. Next question. Must the recovered carbon black be preconditioned prior to feed jet mills?
I don't think so. Normally, it's also, like I mentioned before, the point of the pyrolysis. If you have a continuous agitated pyrolysis, for example, you get a very nice and small feed size out of it, and it can be directly fed into a jet mill. If you have maybe a batch pyrolysis, where very big chunks of tires, for example, are maybe after the pyrolysis are still remaining or are clogging together, then it could be necessary to have a very small pre-grinder before. This could be a simple hammer mill with a high capacity. So this is all preconditioning, I would say, from my point of view, for the size reduction. And other things like volatile content and so on normally should be controlled over the pyrolysis. And after the pyrolysis, it shouldn't be any preconditioning.
Thank you, Christian. Next question. I understand that inerts can be purged from the bottom valve of the jet mills. Can this be fully automated, and would you recommend it?
Yeah, yes, it can be fully automated. Normally, we know it from the mineral industry, for example. For talcum, there's a typical application where we have some quartz in the talcum, and you can see very easily that maybe over 6 hours, the hard to grind quartz is accumulating in the fluidized bed, and then every 6 hours, it's just automatically opened. Then the fluidized bed will be emptied, and then it will be closed again. And then we have much higher quality and much purer quality of talcum at the end. And such a value can also be set for this machine. So maybe it's not for the talcum mills, you have a really set point. If you see a drop down in your throughput capacity, but maybe you can just make it by time. Yeah? If you say every 2 shifts, for example, you just open it, or every shift, or 2 times a shift. It depends how much a product will be in, and then you just open the bottom and you stop the feed for this time, and then you can open it into a big bag or into another containment, and then you can close it and can continue running. This will be easily be automatic possible.
Thank you, Christian. Next question. What is the capacity range of CGS10?
Yeah, maybe okay. Then I put also the next slide. The next slide, which you get later on in the PDF. I just put it into the presentation. So here you see all our CGS types, and you see here the airflow. And the throughput range is very close connected to the airflow. Yeah? And maybe our CGS10, you see also it's our capacity factor 1. This is what we use in our test lab, and there we have 300, maybe 350 kg, for example, for a D99 of 10 micron, and you can calculate down, back, or up over the airstreams what will be here. So the CGS16 is 10 times smaller. This can be easily calculated. So it's maybe 30 kg per hour, and this is maybe even, I would say the half, because it's going very small. So 5 kg per hour, something like that, I would expect for this fine product, if you have nice and pure RCB.
Thank you, Christian. Next question. Are there any dust collecting requirements other than the product collector itself?
Yeah, it depends also on the process. Maybe if we have just very simple flowchart here, it could be that you have some dust emission here, or if you change a big bed that you have some dust emission here. Then normally we have a very small, for example, in the test lab, because we change the products very often, we have small piping here and there just to suck some aerosol just directly away over this. But normally, if you're in continuous running, you have the double flaps here, which is very close, and you have the double flap here, which is also perfectly closed. So normally you have no problems, just maybe by changing your containment, but that depends on the process you have internally in your plant.
Thank you, Christian. Next question. Do you have any operating units in Canada or the USA?
Of course we have, but I think not for the RCB market. I cannot also be so detailed on customers, but I think, as I know, in the US and the RCB market, I think we have not any projects there. But of course, we have a lot of jet mills running in these countries. Yeah.
Thank you, Christian. Next question. Did you study the impact of jet milling on the chemical surface of state of recovered carbon black? Is there any oxidation suspected to occur during the operation?
Yes, we haven't done it so far, but honestly speaking, we are planning together with our colleagues from the thermal gravimetric devices in that. We are planning to make such a campaign, but we haven't done it yet. But also interesting, if a certain customer has interest in, you can also contact me directly, and we can do some trials maybe on a smaller mill, and then together make a functionalization test for the surface. We would be also very interested in such a study. Yeah.
Thank you, Christian. Next question. Is the equipment explosion proof? Is it possible to purge oxygen with nitrogen requested by insurances?
Yes, it's also possible. So pressure shock resistant is not a problem. Although we can also make the execution of the whole mill, like filters and piping, also for the CSM or for the jet mill, pressure shock resistant. And we can also purge nitrogen, and we can also use nitrogen as a grinding media, but this is very, very expensive. Normally, this is done for lab-sized machines. If you do everything in nitrogen, this is possible, but then normally your business case will not work anymore. So pressure shock resistant plants or pressure shock control. So we have, like you see here, a Ventex ventil before the blower. So this will close very quickly if an explosion is detected, and then the whole system is pressure shock resistant. So the double flap valves are safe, and the double flap valve here is safe, and here you close it. So this plant will be inerted, or you also can carbonate it directly with a flask of carbonate. You spray it inside, and you can reduce impact of the shock inside of the filter, for example. But this is not a problem. We can do it for the plant.
Thank you, Christian. Next question. Assuming we operate on a 24/7 basis, how much downtime, uptime should we provision for jet mill?
Yeah, this is also a very feedstock connected question. Yeah? It depends how much silica, even the dirt silica from the streets, which is still remaining, for example, in tires, has a very, very strong impact on the wear, and also the fineness, where it's directly connected to the surface of the product. So if you have a very fine product, you have a high surface and you have higher wear. And I would recommend to use maybe a tungsten carbide wheel in your mill, and then I would estimate very roughly maybe once a year, but maybe 2 times. I think this is, you cannot take my word as a guarantee. It's just my first guess and my impression. So it's a very specific question, but something in this range, 1 or 2 times per year, I would expect. Maybe longer, but yeah, I wouldn't promise too much.
Thank you very much, Christian, for your presentation and also for your time for this Q&A session. And thank you, everybody, for taking part in this session. We would very much appreciate if you could help us keep our service relevant by giving us your feedback. We will send a few questions by email soon, together with a presentation that was shown during the conference. If you want to learn more about these topics, please kindly know that we are issuing a free tire recycling related newsletter once a month. Also in our Weibold Academy section, you will find a wide variety of articles that highlight the different aspects of managing this business. If you have any questions related to the webinar session or our consulting services, please do not hesitate to contact us directly. We are looking forward to seeing you at our future webinars. Thank you, everybody, and have a nice day.